Greetings, I abid to our lecturer Dr. Maman. We are from Group 8, which the members are Norhana binti Muhammad Anwar, Nor Awatif binti Awang, Amira Shazwani binti Saiful Bahri, and I myself, Kalista Abigail Kajetan. Today, our group will present about the seismic interpretation Bandi field. For this presentation, we will talk about the overview of Bandi field, project outcomes, project workflow, methodology, seismic stratigraphy, discussion on findings of the map generated, conclusion including the reference. For this project, Bandi field is chosen as the study area. Bandi field is located at the Malay Basin, the southern part of the Gulf of Thailand, which located between Vietnam and Peninsula Malaysia. Bandi 1 and South Bandi are two wells that are used to further study the geological surface of Bandi field. Bandi 1 and South Bandi are two wildcat wells that were set up and drilled it back in 1990 by EPSI ESO Production Incorporated to test the hydrocarbon potential and reservoir quality within Bandi field area. Bandi 1 well is located approximately 280 km north-northeast direction, while South Bandi well is located 275 km north-northeast direction, both from Kemaman supply base. In tectonic settings, as what we have been studying, both Bandi 1 and South Bandi structures were formed by a combination of structural events occurring during extensional and compressional phase of the structural history of Malay Basin. It was found there is a rise of the formation of half grabens in early extensional phase during Oligocene, though it was not clearly seen in South Bandi due to the poor seismic resolution. As for the stratigraphy in Bandi field, Bandi 1 is planned as a deep well to test porosity development in basin margin position on strike wave. On the other hand, South Bandi is well that was drilled primarily to test the hydrocarbon potential. The section in this Bandi 1 and South Bandi are made up of sandstones interbedded with shells and siltstones. As we can see in the figures, this shows the oil and gas discoveries in the Malay Basin. In the circle is the gas discovery of Bandi and South Bandi. The main objective of this project is to evaluate the geological structure found in the sections of Bandi 1 and South Bandi in the Bandi field. Next, to perform correlation between well data and seismic data from Bandi 1 and South Bandi wells, to generate subsurface map of the Bandi field through seismic and well data correlation between Bandi 1 and South Bandi wells, and lastly, to construct horizon and fault picking as well as horizon and fault interpretation on seismic data of Bandi field. As you can see in the table that is presented in this slide shows our project workflow of this project. In order to generate a time and depth map, first we begin by importing all the data such as well logs data, Bandi 1 and South Bandi, which consists of wellhead and well logs. Other than that, we also import well top and check shots data. Sony log calibration and synthetic generation is conducted by using the Seismic well tie dialog box. Seismic well tie is conducted as to relate the subsurface measurements measured in depth and seismic data measured in time. Picking horizon is conducted at top FSSS as to determine the horizon for every crossline and inline. Then after that, fault picking is conducted by the increment of 50. Surface map then is generated for time domain as well as velocity model in manual and advanced velocity model that can be done in petrol. Depth map is built through the conversion of time to depth map or the generation TZ curve by using Excel. Fault model is generated as to get better illustration of the faults. And lastly, the time and depth map is generated by adding the legends and the color bars as to complete the map.
Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Nur Atif binti Awang and I'll be presenting the part map generation and structural stratigraphy. In the slide, we can see a velocity model time map for Bundy field from section top F. After the horizon was picked and the faults were interpreted on the surface map, it was converted into a velocity model time map. From the colored legend, we can see that the highest elevation, which is negative 1475 ms, orange in color, is centered at the southwest of Bundy Field. It decreases as it makes its way towards the lowest elevation, which is negative 2000 ms, purple in color, at the northeast. The map was contoured at 50 ms interval to get a better picture and resolution of the surface stratigraphy and structure. As seen in the 3D surface map time domain, there are 7 faults that can be identified scattered all around Bundy Field. 6 of the faults were picked at the crossline of the seismic section, while 1 were picked at the inline of the seismic section. The major fault that can be identified would be the fault that is picked at inline 1403, as it is the largest of all faults and the fault is clearly identified throughout the seismic section. From the slide, you can see a 3D surface map of the velocity model time domain of the fault plane. From the slide, we can see a velocity model depth map for Bundy field from section top F. A depth map is used to display the actual depth of the subsurface that has been chosen. This depth map shows the surface with a better image with 50-meter intervals. The surface structure of top F is more visible in the depth map compared to the time map because the depth conversion that is used is able to eliminate the structural ambiguity and demonstrate the surface structure. From the map, we can see that the elevation increases at the east side of the map with the highest elevation of negative 1500 meter, orange in color, and it decreases at the west side of the map with the lowest elevation of negative 2300 meter, purple in color. A depth map is used for further interpretation of seismic section because it is deemed as the most accurate compared to time map. From the slide, we can see a 3D surface map in the depth domain, which is the fault plane. Next is the result and discussion for structural stratigraphy. For seismic reflection, the seismic reflection is assumed to represent the bedding plane. Thus, the characteristic of seismic reflection should change with the conformable changes in the depositional regime. From the seismic data, we have interpreted several depositional regimes, which are first, the reflection continuity. Reflection continuity shows the continuity of layers and is related to the energy level at the depositional environment. In our case, the reflection continuity is very high in continuity. Second is the reflection amplitude. Reflection amplitude shows the lithology contrast, bedding spacing, and fluid content. In our case, our reflection amplitude is moderate to high in amplitude. Third is the reflection configuration. Reflection configuration shows the geometry of bedding pattern, which is important to interpret paleogeography. In our case, our reflection configuration is parallel. Fourth is the reflection frequency. Reflection frequency shows the thickness of the bed. In our case, our reflection frequency or our bed thickness is very low in frequency. From the generated seismic data, we can observe the bounding relationship between the sedimentary planes, which are continuous and draping underlying topography. Thus, from all of the indicators that we have, we can interpret our depositional environment as pelagic or hemipelagic.
Hello sir, my name is Norhana and I'll be presenting about the picking of horizon, fault interpretation and also faults. For our horizon, we have peaks along the horizon top FSST made up of sandstones that starts from a depth of 1629 meters. As you can see, the blue line is the horizon that we have picked, while the green line across the seismic section is the fault interpretation. On the slideshow right now is view of our surface map from the top view. We are viewing our picking from the inline for the horizon, while this one is the picking of the horizon at the cross line. For horizon interpretation, it is an important step in seismic interpretation before any maps are produced. It is made based on well-thought data that has been interpreted throughout well-log correlation. For our study, a horizon was picked which is at the top of group F. There's also other horizons which is E32 or H. According to the well report, the depth of group F is around 1,629 meters from the surface. Horizon picking were made for every 50 intervals for both cross-line and inline. The intervals are suitable and accurate enough for the structure of the field. If the structure of the field is more complicated, the intervals could be reduced so that we can get more accurate results. As we can see in the diagram, this is the top view of Bundy Field, which has the surface map as well as the horizons that has been picked and with the faults. We have in total 7 faults that we have found in our seismic section. We have categorized the faults according to where we have picked them, which we have picked 6 at the X line and 1 in the in line. On this slide, we could see the complete overview of all the faults that were interpreted and also the horizons that we picked. For each fault, we could see the dip angle, the strike, the dip azimuth, displacement, and length of faults. For the dip angle and strike, it gives us the direction of the line formed by the intersection of a fault, bed, or other planar feature and a horizontal plane. Dip is the acute angle that a surface makes with a horizontal plane. From the data of length of faults, we could see the largest fault is fault in line 1403 with a distance of 6,536.84 meters, which is probably due to the tectonic history and events that has happened during the construction of Malay Basin. For the displacement, fault in X line 1659 has recorded the largest displacement, which is 199.14 meters. This is all due to the combination of structural events occurring during extensional and compressional phase of the structural history of Malay Basin. In this slide, we'll be discussing the faults resulting in horse and graben structure. From the seismic section displayed below, the two faults are dipping towards each other that can result in a horse and graben structure. The fault in the left side, which is the green line, is the fault cross line 3009, while the fault on the right represents fault cross line 2559. Both of the faults are normal faults. Horse and graben is a type of topography that will form when the Earth's crust is being pulled apart. The process is identified as an exsection, and it can totally stretch the crust until 100% compared to its original size. Horse and graben, being this shape, it can also serve as a good structural trap for hydrocarbon exploration. Moving on to faults that we have found in the seismic interpretation Bundy field, it is defined as a wave, like geological structure, that forms when the rocks deform by bending instead of breaking under compressional stress. There are 3 main forms of faults: syncline, anticline, and monocline. For our seismic interpretation, we have only found anticline and syncline, which will be seen in the diagram on your right. The faults in the seismic section figure on the right may be directed to the faults, which we call these faults as the fault bed faults. The Bundy prospect is relatively of low relief anticline that is often associated with major northwest southeast trending basement. As we can see on the diagram, there is an anticline on the left circle and a syncline on the right circle.
Hi sir, my name is Amira Shazwani and I will present about sequence stratigraphy. Based on this slide, we can see that we can differentiate each sequence based on their amplitude and frequency. So for sequence 1, it has high amplitude and high frequency. Sequence 2 has medium amplitude and medium frequency. Sequence 3 has high amplitude and high frequency. Sequence 4 has low amplitude and low frequency. Sequence 5 has medium amplitude and medium frequency. And lastly, sequence 6 has low amplitude and low frequency. This sequence stratigraphy can be measured by looking at the changes of amplitude and frequency. High amplitude is when the color of lines are vibrant, which is in red or blue color, while high frequency can be identified when several lines are located close to each other. For termination of strata, figure on the right shows one of the example of top lap and down lap that we can see in the map. So what is down lap? Down lap is the stratal termination down against the underlying strata that has low apparent dip, and top lap is the stratal terminations of younger reflections against the overlying surface, mainly resulting of non-deposition with perhaps minor erosion. Next, I will present about channel. So, channel systems are major places of gathering the hydrocarbon due to high permeability. Porous and permeable media could fill the channels and form high quality reservoirs. So based on these two figures, these are two examples of channel that we can found in the map. So it is identified by unusual V-shaped depression. The height is estimated to be around 30 meter. The channel is characterized by high amplitude reflection (HAR) on the channel margin, which signifies that the turbidity currents were vigorous and intense. This is what we can see at the z-line of -100. We are able to identify the structure of a Mandarin channel and the makings of an oxbow lake in the seismic section. There are parts of the channel that has a high sinuosity, which is highlighted in yellow, others which are straight, which is highlighted in red.
In conclusion of this project, from the Bundy field, seismic interpretation can be done using Petrol software in deducting its surface features, stratigraphic elements, structural challenges, due to the various range tools that are available. Petrol has given us stratigraphic features such as termination of strata, faults, and the elevation through depth and time map in order for us to understand the area further. For better resolution of faults and horizon of the surface map, an increment of 50 or lower could be used in both inline and crossline. The time map gives us the elevation in terms of velocity, while the depth map display a better understanding of the area and surface structure in comparison to time map. From structural and stratigraphic features of Bundy Field, it can be seen as potential hydrocarbon field for commercial exploration. And that is all from our group. Thank you.